All right, welcome to this explainer on the modeling of hydraulic systems, all based on the fantastic work prepared by Dr. Nima Madian. Think of this as a rigorous but totally manageable journey, taking us from the raw 3D physics of fluid dynamics straight into the elegant architecture of digital control logic. You know, if you've ever wondered how engineers tame physical chaos into precise mathematical models, well, grab your calculus toolkits. Let's dive right in.
So here's our syllabus for this explainer. We're going to cover the baseline valve control system, the pump control paradigm, continuity and fluid physics, linearizing pump dynamics, assembling the differential equation, and finally, we'll wrap up in the Laplace control domain.
Section 1, Baseline Valve Control System.
Okay, first, let's visualize our physical reality here. Just take a look at the heavy steel tank holding our fluid. You can see the churning industrial pump, the whole complex network of pipelines, pressure gauges, the manual valves. It's a lot, right? But remember, every single piece of math we discussed today is explicitly anchored right here to these exact real-world physical components.
Now, simplifying that really complex 3D reality, our fundamental engineering goal is actually pretty straightforward. We literally just want the actual fluid level, let's call it L, to perfectly match a desired target level, LD. Historically, well, we achieve this regulation just by mechanically throttling that outflow valve you see at the bottom right. The controller basically measures the tank level, compares it to our target, and just physically turns that valve. Pretty simple.
So mapping those physical components directly into our control logic, let's follow the feedback loop. Starting on the left, our target level, LD, hits a summing junction. It's comparing it against the actual measured level, L. The controller reads this error and boom, applies a corrective action. That's block A, right there, adjusting the valve aperture. Then, the block 1 over S plus lambda simply represents the physical tank reacting and establishing the actual fluid level. It's just a simple continuous loop.
Moving on to Section 2, the pump control paradigm. Now, understanding exactly why we're shifting away from those simple valves is absolutely crucial. See, with valve control, our control variable was output flow, actuated by mechanical throttling. Simple, sure, but it wasted a ton of energy. With pump control, our variable flips to input flow, actuated by changing the rotor speed. It's an absolute game changer. It's the standard for modern high-efficiency systems. But notice the trade-off here. By doing this, we inherit a massive, highly nonlinear mathematical headache.
Rather than choking the output flow to control the tank level and wasting all that energy, we are now actively spinning the pump rotor to directly inject input flow, Fin, into the top of the tank. By regulating the speed of the rotor, N, we save tremendous amounts of energy. But, and it's a big but, injecting flow dynamically like this introduces those highly nonlinear fluid dynamics directly into our control loop. We can't just open a valve a little bit more anymore. We actually have to command a spinning rotor that is actively fighting against fluid pressures.
Which brings us to Section 3, Continuity and Fluid Physics.
Okay, so the fundamental continuity equation dictates a perfect mass balance. Fin minus Fout equals A times the derivative of L. So what does this actually mean? Well, Fin is the fluid our pump pushes in, and Fout is the fluid naturally exiting. The difference between those two must equal the cross-sectional area of the tank, A, multiplied by L dot, which is just how fast the surface level is moving up or down. You literally cannot cheat this physics. It is absolute.
But here is exactly where that continuity equation gets messy. That Fin we just talked about, actually, let's call it the flow delivered by the pump, it isn't just some arbitrary number we can dial in. If we examine these complex curves of pump performance, which by the way define the actual output after manufacturing and testing, you'll see the output flow of the pump, FO, is a coupled, completely nonlinear function of both the resisting pressure head, P on the y-axis, and the rotor speed, N. As pressure goes up, flow drops off along a curve. And if you change the RPM from, say, 1,000 to 1,400, you jump to an entirely different curve altogether. It is this massive, interlocking, nonlinear web.
But don't worry, we have the tools for this. Section 4, Linearizing Pump Dynamics.
To actually tame this nonlinear chaos, we apply a really powerful tool from calculus. We don't actually need to model the entire curved operating range. By focusing on a nominal operating point, N star, P star, we zoom in close enough that the curve essentially looks flat. Utilizing a first-order Taylor series expansion, we can redefine flow entirely in terms of small deviations. So, delta FO equals the partial derivative of flow with respect to pressure times delta P plus the partial derivative with respect to speed times delta N.
Let's just dwell on this derivation for a second, because it's important. Step 1.
Identify the nonlinear operating point. Step 2, apply the Taylor series expansion. And step 3, extract those messy partial derivatives and simply rename them as constant coefficients, alpha and beta. Just like that, we have successfully transformed a chaotic 3D curved surface into manageable, localized linearity. We are now dealing only with small, highly predictable deviation.
So how do we actually find alpha and beta in the real world? Well, we extract them graphically, right, directly from our empirical pump testing data. In the first panel on the left, pressure sensitivity, our alpha, is evaluated literally as the tangent slope of the nominal speed curve exactly at our operating point. You just draw a straight line against the curve and measure the slope. Then, in the second panel on the right, speed sensitivity, or beta, is found by drawing a horizontal line of constant pressure and measuring the gap, the flow variation, between two adjacent speed curves. It's real-world testing geometry perfectly yielding our required mathematical coefficients.
All right, let's put it all together. Section 5, assembling the differential equation.
We need one final puzzle piece to connect the tank back to the pump. Visualize that rising column of water in the tank again. As that fluid level rises, it pushes down, creating a direct hydrostatic pressure against the pump that's trying to fill it. We call this the hydrostatic link. The pressure variation, delta P, is simply the fluid density, rho, times gravity, g, times the actual level variation, delta L.
To formally define it, the hydrostatic link is the fundamental principle dictating that the pressure resisting the pump is not some arbitrary force. No, it is strictly and physically dictated by the fluid's density, gravity, and the actual varying height of the fluid inside that tank. Any variation in fluid level instantly generates a variation in the pressure fighting the pump. The whole system is completely interconnected.
Now we assemble our master equation. Trace the logic downward with me here. We start with our continuity equation. We substitute our linearized pump dynamics in for delta FO. Then we look at our hydrostatic link and substitute rho g delta L for the pressure term. And there you have it. This elegantly combines our mass balance, our pump dynamics, and our fluid head pressure into one single master time domain differential equation.
Finally, the payoff. Section 6, the Laplace control domain.
To actually build our digital controllers, we need to shift out of the messy time domain T and into the clean frequency domain S, using the Laplace transform. Time derivatives basically turn into straightforward algebraic S variables. Rearranging the terms yields this pristine formulation. It beautifully isolates our fluid level variation, delta L, purely as a function of the external system disturbance, delta Fn, and our active control variable, which is the pump speed variation, delta N. And this right here is the complete pump-regulated control block diagram. Walking through this ultimate feedback loop, our desired target level LD creates an error signal. Our controller calculates a voltage V. Then, the physical pump translates that voltage into rotor speed, which gets multiplied by our speed sensitivity beta. It actively fights against physical disturbances, passing right through the tank's physics, so gravity, density, area, and pressure sensitivity alpha. Physical constants and empirical data are now perfectly integrated into a precise control architecture. Let's just take a step back and summarize this grand intellectual journey we've just taken, what I like to call the executive synthesis. Step 1. We anchored ourselves in fundamental 3D physics, choosing high-efficiency pump actuation over wasteful valves. Step 2. We completely conquered the nonlinear fluid dynamics by utilizing Taylor series expansions to transform curved surfaces into localized linear tangent geometries. And Step 3. We synthesized all of that into the Laplace domain, isolating disturbances to engineer perfect stability. Guys, this is the definitive translation pipeline from a heavy physical asset into a precise digital twin. Which leaves us here with a real question to ponder. How will mastering this exact physical to digital translation pipeline completely transform the way you architect your next complex industrial control system? The math is no longer an obstacle, it's the exact tool you use to tame reality. I really hope this explainer illuminated the incredible structure behind modeling hydraulic systems. A huge thanks to Dr. Nima Mahian for preparing this material. Thank you so much for joining me, and I'll catch you on the next deep dive.